Our first strategy is to use Monte Carlo Learning. Recall the incremental step that is used in classical Monte Carlo Learning to update value functions. Here GT is the return, that is the cumulative discounted reward received following time t. That's a suitable target to attain, isn't it? So let's take our neural network update rule and simply substitute the unknown true value function with this return. This gives us a concrete update rule for state value functions represented by neural nets or other function approximators. As you might have guessed, we can do the same for action value functions as well. Now that we have the main building block, the update rule, let's build a complete Monte Carlo algorithm around that. Let's focus on the control problem and adapt our classic Monte Carlo algorithm to work with a function approximator. It generally includes an evaluation step where we try to estimate the value of each state action pair under the current policy. We do this by interacting with the environment to generate an episode using the policy pi, and then for each time step t in the episode, we update the parameter vector w using the state action pair stat and the return gt computed from the remainder of the episode. This is followed by an improvement step where we extract an epsilon greedy policy based on these q values. At the beginning, we need to initialize our parameters w, let's say we do that randomly, and start with a policy pi defined in the same epsilon greedy manner. Then we can repeat these two steps over and over till the weights converge, resulting in the optimal value function and hence the corresponding policy. Note that this is the every visit version of Monte Carlo. For the first visit version, you only perform the weight update when you see the state action pair for the first time in an episode.